Special values of complete elliptic integrals of first and second kind. In my previous video, I basically found the values of the complete elliptic integral of first kind at I and the complete elliptic integral of second kind at I. Yeah, and you can check this in my playlist of the elliptic integrals, which I link over here. Yeah, and if you don't know about the elliptic integrals in the first place, let me just define it. The complete elliptic integrals of first kind of M is defined as integral from 0 to pi by 2 of 1 by root under 1 minus m square sine square theta d theta. Yeah, and E of M is defined as integral from 0 to pi by 2 of square root of 1 minus m square sine square theta d theta. Okay, fine. Now we will just go with the definition and try to find the values. It's not that hard. So let's try to find k of 1 by root 2. Yeah, k of 1 by root 2. We know that this is integral from 0 to pi by 2 of 1 by square root of 1 minus its square is 1 by 2 and then sine square theta and d theta. Yeah. Now if we let y equal sine square theta, we get integral from 0 to 1 by root under 1 minus 1 by 2y square, and also since y equals sine theta, theta equals to sine inverse y, that's why we have 1 by root under 1 minus y square dy. Is that? Yeah, fine. Now the next thing will be we will take 2 over here, and that gives us integral from 0 to 1 root 2 by root under 2 minus y square root under 1 minus y square dy. Now to simplify this, what we can do is we can let g equals to 1 minus y square. Yeah, because that will simplify this expression. This will be 1 minus something, and this will also be simplified, and 1 minus something and something can be in terms of beta function. Yeah, that's why. Now this gives us y square equals to 1 minus g, y equals to 1 minus g to the power 1 by 2. Yeah, and this will be basically from 1 to 0. Now root 2, this will now be 1 plus g, and this will be g, and dy will be 1 by 2 1 minus g to the power minus 1 by 2 and then minus 1 dg. Now minus 1 will reflect the integral back to 0 to 1, integral from 0 to 1, and over here it's root 2 by 1 by 2, so that's 1 by root 2, and over here we have root of 1 plus g, we have 1 minus g to the power minus 1 by 2. So this to multiply to give 1 by root under 1 minus g square, and then 1 by root g dg. Yeah, that's fine. Now what's next? 1 by root 2 integral from 0 to 1. This is actually g to the power 1 by 2 1 minus g square to the power 1 by 2 dg. Yeah, it's in form of beta function, but first let us change this g square to, let's say, x equals to g square. That gives 1 by root 2 integral from 0 to 1 of, now this is x to the power 1 by 4, and then 1 minus x to the power, this is 1 by 2, and then 1 by 2 x to the power minus 1 by 2 dx. Yeah, from here. So now this is 1 by 2 root 2 integral from 0 to 1. Now this is x to the power minus 1 by 4, isn't it? Yeah, and 1 minus x to the power 1 by 2 and dx. Okay, after this we can find this in terms of beta function. 1 by 2 root 2, this is beta of 3 by 4 comma, is this 3 by 2? I wasn't expecting this. This is minus 1 by 2 actually. So this is minus 1 by 2. This is also minus 1 by 2. I'm sorry. Now this is minus 1 by 4. Yeah. This is also minus 1 by 2. I'm really sorry for all these mistakes. Minus 1 by 2. This is minus 3 by 4. Okay, fine. Now this is beta of 1 by 4. Fine. And this is 1 by 2. Now the answer is 1 by 2 root 2 gamma 1 by 4 gamma 1 by 2 by gamma 3 by 4. Multiply by gamma 1 by 4 in numerator and denominator. Yeah. And from reflection formula we can, sorry, not by 1 by 2, 1 by 4 I say. Now after we do this, we can basically use the Euler's reflection formula. Yeah, and because here's a and over here 1 minus a, so we know that gamma of a, gamma of 1 minus a is basically pi by sine pi a. That's why using this reflection formula we get 1 by 2 root 2. This is gamma square 1 by 4 by root pi, and this is pi by sine pi by 4. That's 1 by root 2. So this is 1 by 4 root under pi of gamma square 1 by 4. Yeah. So we found the first value by simple integration methods. Yeah. 1 by 4 root pi gamma square 1 by 4. Yeah. So we basically made unit substitution, and then over here we tried to simplify it by changing g equals to 1 minus y square, then multiplied and beta function unit substitution and did this stuff. And here you should also notice something, that in my previous video when I was finding k of I, the value was 1 by 2 root 2 pi root pi times gamma square 1 by 4. Yeah, and in this it's just k of 1 by root 2, it's just 1 by root 2 times k of I. And do you suspect any other relations that makes this true? So yeah, there's an identity that I have already discussed in this series of elliptic integrals. Yeah, and that a special identity, which is the k function of root under let's say m by m minus 1. This is actually equals to root under 1 minus m times k of root m. We proved this identity as well. Now using this identity, if I put m equals to minus 1, what do we get? Over here this is minus 1 by minus 2, so that's square root of 1 by 2. K of square root of 1 by 2 is equals to, and then this is root 2, and then we have over here k of square root of minus 1 is I. So you can now see why this holds true. K of I is equals to 1 by root 2 of k of, wait a second, here's it's something different. Wait, so k of is written to 1 minus m times k of root k. Wait. So over here this was q of I was this thing, yeah, and q of 1 by root 2 is 1 by root 2 times q of I. But here's is something different. So I put m equals to -1, so root 2 times q of I, q of 1 by root 2, so q of I equals to 1 by root 2 times q of I, root 2 times q of 1 by root 2. Is that what we were expecting? But no, that was not what we were expecting. Just give me some time. Q of 1 by root 2 was 1 by 4 root pi. Oh. I missed it. I guess. Q of 1 by root 2 is 4 root pi. Yeah. So to get that, we should basically multiply this by 1 by root 2. K of I by 1 by root 2, yeah. And now we have this identity. K of square root of m by m minus 1 is equal to root 1 minus k times k of root m. Yeah. If we get -1 in that, we get k of I equals to k of 1 by root 2 equals to square root of 2 times k of I, and then k of I equals to 1 by 2 times k of 1 by root 2. Oh, the problem is this is not 2 root 2. Okay, so this was fine. Nothing happens. This is not root 2. K of I was 1 by 4 root 2. I'm sorry for that, and that's why this is not root 2 over here. It's actually in the numerator. Okay, root 2. Now this looks fine, yeah. So now this works. So K of 1 by root 2 is equals to root 2 times k of I. Fine. It works. I actually put the wrong value. Now similarly, for the second one, you can go in the similar approach. It's nothing different. Basically, in my other videos, I've also found E of I. Yeah, and you can also check that how I have done there, and also this one. And merging these two, you can solve the second one as well. But for now, like, I will use this approach, yeah, for finding E of 1 by root 2. Basically know that E of square root of m by m minus 1 is 1 by, it's just the reciprocal, root under 1 minus m times E of root m. Yeah. And we know that E of I was basically, what was it? 1 by 4 root 2 pi on gamma square 1 by 4. I have already derived this one in previous video, plus 1 by root 2 pi times gamma square 3 by 4. This is E of I. Now we know from this formula that E of 1 by root 2, yeah, if we put m equals to -1, is equals to, this is 1 by root 2 times E of I. Yeah, now put 1 by root 2, that gives us 1 by 8 square root pi of gamma square 1 by 4 plus 1 by 2 root pi of gamma square 3 by 4. Yeah. So that is it. We have also found its value. And if you want the derivation of this formula, do check my playlist. I have already derived this manually using by going through all the integration process. Yeah, hope this makes sense, and yeah, hope you enjoyed the video. And yeah, it was fruitful to learn something new, and look forward to seeing you in the upcoming videos too.